Hey everyone, and welcome to today's Explainer. We're going to be diving into a seriously fascinating algorithmic puzzle today, one that actually pops up a ton in coding interviews. We're talking about the longest increasing path problem. It's this really elegant mix of grid traversal and dynamic optimization. So let's crack it together.
To really get the intuition behind this problem, I want you to imagine you're mountain climbing. But instead of a rocky mountain, you're standing on a flat grid of numbers. You want to take steps, moving from cell to cell, but the absolute golden rule of this hike is that you can only move to higher ground. You can never step down, and you can't even step sideways onto a flat plane with the exact same elevation. The question is, how do you find the absolute longest continuous uphill path?
Okay, let's look at this 3x3 matrix filled with positive integers. This right here is our mountain. Our goal is to find the longest, strictly increasing sequence of numbers. We can move four ways: up, down, left, or right. Notice how we could start at the 1, move down to the 3, right to the 4, up to the 5, and finally right to the 8. That gives us a continuous sequence of 5 cells. And it actually happens to be the longest possible uphill path you can take in this specific grid. So here's our logical roadmap. We'll start with the matrix maze problem, move into the DAG revolution, then traversing with DFS, followed by the memoization optimization, and finally a quick complexity breakdown.
All right, let's kick things off with section 1, the matrix maze problem.
Let's lay out the ground rules for this puzzle. First up, we've got total freedom of origin, meaning we can start our path at literally any cell in the entire matrix. Second, from whatever cell we're on, we can only move 4 directionally, so up, down, left, or right. No diagonal shortcuts allowed here. And third, and this is absolutely crucial, the path has to be strictly increasing. I really want to highlight that word, strictly. That means we cannot step onto a cell with an equal value. If you're on a 4, you cannot step onto another 4. You always have to climb higher. Which brings us to section 2, the DAG revelation. Changing our perspective here is a total game changer. To really get this revelation, we first need to quickly define a DAG, or a directed acyclic graph. Think of the grid cells not just as little boxes, but as nodes in a graph. The directed part means the moves between these nodes are strictly one-way streets. Because we can only ever move from smaller numbers to larger numbers, the connection is always directional. And acyclic simply means there are no cycles, no loops. Since we're always climbing up in value, it's actually physically impossible to loop back to a cell we've already visited. I mean, you can't climb uphill and somehow end up back where you started without taking a downward step, right? Now, check out this transformation. It's kind of like putting on a new pair of glasses. We've got our standard matrix, but then we map it out into a graph. We treat the matrix cells as nodes and the valid uphill moves as directed arrows or edges. Suddenly, we aren't just staring at a grid of numbers. We're looking at a directed acyclic graph. This is a massive breakthrough because finding the longest increasing path in a flat matrix is, under the hood, the exact same task as finding the longest path in a DAG. Okay, section 3, traversing with DFS. Now that we know we're dealing with a graph, we need a reliable way to explore it. One really straightforward strategy is to just find the length of the longest path starting at every single cell, and then, well, just pick the biggest number. To pull that off, depth first search, or DFS, is absolutely our tool of choice because it's just so elegant for pathfinding. We just kick things off by initiating a DFS call right at the top left cell, coordinate 0, 0, which holds the value of 1. Let's watch how this branches out. To figure out the longest path from our starting 1, our DFS algorithm has to check out its neighbors. But remember, it only cares about the valid higher value neighbors. The 1 can move down to the 3 or right to the 5. So by making a recursive DFS call to each of these larger neighbors, we can discover the lengths of the paths that unfold from them. The longest path starting at the 1 is just going to be whichever of those subsequent paths is longer, plus 1 to account for the starting cell itself. So let's distill that logic into 3 easy steps. Step 1, identify all higher value neighbors from where you are. Step 2, make a recursive DFS call to each of those neighbors. And step 3, return the maximum path length you found among them, plus 1 for your current cell. And honestly, here is one of the coolest perks of knowing this is a DAG. We don't even need to maintain a visited set to mark cells we've already stepped on. Because the path is strictly increasing, a cycle is literally impossible. We can't step on our own toes even if we tried. Moving right along to section 4, the memoization optimization. So our DFS works perfectly. But
We are about to face the final boss of recursive algorithms, redundant computations. I want you to take a close look and see if you can spot the trap here. Look at the cell holding the number 9, down in the bottom row. Because we're initiating a DFS from every single cell, our algorithm is going to stumble onto this 9 from a bunch of different starting points. A path from the 7 ends up calling DFS on the 9. A path from the middle 4 calls DFS on the 9. And a path from the 2 calls DFS on the 9. We are calculating the exact same longest path originating from that 9 on 3 completely different occasions. In a huge grid, doing that over and over would be computationally devastating.
So, how do we fix this mess? With a little principle I like to call compute once, remember forever. This is memoization in a nutshell, and it's basically the ultimate algorithmic life hack. Once we calculate the longest possible path starting from a specific cell, like that 9 we just looked at, we simply store that result in a table. If any future DFS search stumbles onto that cell again, we don't do all that math again. No way. We just instantly return that saved result. It short-circuits all that massive redundant branching and saves us an enormous amount of time.
Finally, let's wrap up with Section 5, complexity breakdown. Let's crunch the numbers and see how this actually performs. The big takeaway here is that without memoization, our time complexity would be completely astronomical. But with it, our time complexity is beautifully optimized down to big O of m times n, where m is our rows and n is our columns. Why? Because every single cell in the matrix is visited at most twice. Once when we do our initial loop to start a path, and once during the DFS traversal. After that, memoization instantly handles any future visits. Now, as for space complexity, that also sits at big O of m times n. This is that classic computer science trade-off, right? We're trading memory for speed. We need that extra space for 2 main reasons. First off, the recursive call stack during our absolute deepest possible DFS traversal could theoretically string through every single cell, growing to m times n. And second, that life-saving memoization table where we stash all our results, that also scales perfectly to the size of the grid, which is, you guessed it, m times n.
And that brings our traversal to an end. We took a raw matrix, realized it was secretly a directed acyclic graph, unleashed a depth-first search on it, and supercharged the whole operation with memoization for a brilliant O of m times n solution. I'll leave you with this final thought to chew on before your next coding session. Look closely at the constraints of the next puzzle you face. What other wildly complex grid problems out there can be radically simplified just by mapping them to a DAG? Keep an eye out for those hidden graphs, focused learners. Thanks so much for joining me on this explainer, and keep exploring.